Hi everyone, welcome to the continuation for our lecture on section 11.2 on the properties of power series. In this video lecture, we're going to be continuing where we left off and discuss more properties of power series. Now the last example that we worked on in class here was a problem that was asking us to use the Maclaurin series for e to the x to find the Maclaurin series for e to the 2x. In class, we worked on this example backwards as a way of reviewing how to figure out a Maclaurin series, or a Maclaurin polynomial in this case, although we did continue on to infinity. Now, the way that we did it here, well, we come up with our formula here, remember. Well, we reviewed it here on section 11.1, but we came up with the following series. It was the sum as n goes from 0 to infinity for negative 1 to the n times 2 to the n times x to the n, which was nicely abbreviated here as the sum as n goes from 0 to infinity for negative 2x to the n over n factorial. However, as mentioned in class, we don't really need to do this process because, well, if we happen to know the Maclaurin series for e to the x, which I wrote down here, we can take advantage of the fact that one of the properties for power series is that we can treat them here as a function composition. So what we did in class towards the end here was to say that, okay, well, if I know that the power series for e to the x is the same thing as x to the n over n factorial, well, we can easily treat this one here as essentially the function composition of e to the u, and treat this one here as the power series as n goes from 0 to infinity for u to the n over n factorial. Now, because in our example here our u was negative 2x, well, then we can just go ahead and plug in this 2x into our function, our power series, and we'd be done. Now, the other example that we did in class here towards the end was, okay, well, what about the power series for x to the 4th times e to the x? Well, in that scenario here, we can easily treat it here as x to the 4th times the power series representation for e to the x. Now, at this point here, we can just bring in the x inside the series, multiplied here x to the 4th times x to the n. Now, using the properties of exponents, we're just going to have here x raised to the n plus 4 divided by n factorial, and that here would finish the problem. Much easier than figuring out, okay, what would be the Taylor polynomial for x to the 4 times e to the x. Because now we can we can basically avoid this process of finding the derivatives and evaluating them at the x that you're centered at. Okay, so we're going to continue on with more properties of power series, but this time around we're going to be combining our knowledge from calculus here. And we're going to see here that we can actually go ahead and differentiate power series and integrate power series, because again, we're saying here that a power series is another representation for a function. Alright, so suppose that we have a power series that converges for some interval and it's defined a function on that interval. Then f is differentiable, which implies it's continuous, for that same interval, and f prime, the derivative, is found by differentiating each term of the power series. So that means that if we're going to find the derivative here for a power series, we need to differentiate term by term. Now, this one here, this derivative, is going to be existing for that same interval as the function. Now, the definite integral for f is found by integrating the power series once more, term by term. So we're going to be defining here the integral for f of x dx, and this one here, again, since the power series, well, it's called power series because we just have a function of x raised to a power, so we're basically using the power rule for antiderivatives, and that is going to give us the antiderivative for the function on that same interval. Now, what I want you to note here is that the radii for convergence for the power series in equations 1 and 2, they're both r. So if you figure out the radius of convergence for the function, if it's that it's r, then that's also going to be the radius of convergence for the derivative and the integral. However, this does not mean that the interval of convergence is the same. It may happen that the original series converges at an endpoint, whereas the differentiate or integrated series diverges there. So we would still need to check the endpoints. Okay, so let's practice here with a couple of problems. And let's begin with example 4, when we're being asked to use the Maclaurin series for sine of x, and use that to find the Maclaurin series for the cosine of x. And again, there's another typo here, guys. Let's get rid of it. There we go. Okay, so let's use the Maclaurin series for sin of x to find the Maclaurin series for cosine of x. Okay, so for this problem here, guys, I'm just going to jump straight into the Maclaurin series for the sin of x. Now, I asked you guys to work on it in the video lecture for section 11.1, so hopefully you got it, but if you didn't, this is the Maclaurin series, and I'm going to go to only fourth terms. So we're going to have here, the sin of x is the same thing as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and we would keep on going here. Okay, now let's go ahead and use this series to get the Maclaurin series for the cosine of x. Now, how can we do it? Well, we know that the derivative for sine is the cosine of x. So basically, what I'm going to be doing here is I'm going to go ahead and take the derivative for each individual term here. There's 4 terms here. So we're going to get the derivative for x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. And it keeps on going here. Alright, so taking that derivative, we're going to get a 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. And we would have kept on going here. Now at this point, I'm going to go ahead and simplify because I have a couple of factorials in the denominator. Now I know here 3 factorial is the same thing as 3 times 2 factorial. 5 factorial is the same thing as 5 times 4 factorial. And 7 is the same thing as 7 times 6 factorial. Now we get to see here that, okay, well, I guess I can cancel some of the factors here. The 3's cancel, the 5 cancels here, the 7 cancels here. So we're left with the following. 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. And of course, we would continue on. Now, does this series look familiar? I hope so, because we already encountered this series all the way back in our section 11.1 when we were discussing the Taylor polynomial, more specifically the 10th order Maclaurin polynomial for the cosine of x. And there we go. It is the same thing, except that on this example we went all the way till x to the 10 over 10 factorial. But going back to our example here, this one, since we can also rewrite it as a series, this one is going to be the same thing as the infinite series here as n goes from 0 to infinity for, we're going to have a -1 factor since it's alternating sign, -1 to the n times x to the 2n over 2n factorial. And there we go. Perfect. So now you get to see here that they are different ways of getting other series representations for functions. We can use derivatives and integrals. Now, speaking of integrals, let's take a look at another example here. Now, this one here, I try to do something different. This time around, we are dealing with a word problem, and we're going to appreciate here how power series can come to the rescue to evaluate integrals that we might not be able to integrate with the techniques that we've seen so far. Alright, so let's take a look at the problem. So we have here that a country is predicted to have an excess of sine of t over t million births per year. Now, this is above the usual level in year t. Now, during the first x years, this means that an additional quantity given here by the integral from 0 to x for sine of t over t dt, million births. Now, we want to go ahead and find the Taylor series for this integral, and then use this series to estimate the number of extra births during the first 2 years. Okay, so right now, if we went ahead and simply try to go ahead and figure out what is the integral for sine of t over t dt, we really wouldn't be able to figure out this integral. So we cannot integrate it with the techniques that we've seen so far. In fact, this is a special integral that you really cannot find an answer nicely. So here's the trick that we're going to be using. We're going to go ahead and rewrite this integral as a power series, or the integral of a power series. Okay, so let's go ahead and do that. I'm just going to go ahead and move this one here. Alright, so we're going to have here the integral from 0 to x. Now, I'm going to go ahead and break this up. I'm going to think about the sine of t over t as 1 over t times the sine of t. But the sine of t is the one that I'm going to go ahead and rewrite this one here as a power series. Now, the power series for sine of t, we just discussed it. It's going to be t minus t cubed over 3 factorial plus t to the 5th over 5 factorial minus t to the 7 over 7 factorial. and it would have kept on going here, dt. Okay, so now before performing the integral, I'm going to go ahead and multiply everything by a 1 over t. So what is that going to give us here? Eventually we would have multiplied times every single term. So this is going to give us then the integral from 0 to x for t times 1 over t is just going to be 1, and then we're going to be getting the rest of the integral here. Okay, so now that we've simplified it, let's go ahead and get the integral now. So getting the integral, we're going to get here, let's see, the integral of 1 is just going to be a t minus t cubed over 3 times 3 factorial plus t to the 5th over 5 times 5 factorial minus t to the 7 over 7 times 7 factorial. And now we're going to be evaluating this one here, although, let me clarify that this one here would have kept on going, and we would have been evaluating all of these terms at 0 and at x. So that means that we would have gotten the following. Now I'm just going to go ahead and rewrite this expression in terms of x now. So that's just going to be same expression, just replaced with the x's. Okay, now we're being interested, or we're focusing on right now, okay, what's going to be the extra births during the first 2 years. So letting x equals to 2, if I plug it in, I'm going to get, now I'm not going to go ahead and write the whole thing, guys, but if I let x equals to 2, then our sum here is approximately, I got 1.605, but we're talking about our quantities here in terms of million. So 1.605 million births. Now, is this a good approximation? I would say so, because we know that the radius of convergence for sine of x is all real numbers. So this power series will be converging to sine of t over t. Now, notice here that I only went up until 4th terms, essentially 7th order here. Could we have done more terms? Yes, we can, but if we would have kept on going, notice the next term here would have been then an x to the 9th over 9 times 9 factorial. If you put this one here into your calculator, this is a really small number. If we went up to one more term, x to the 11 over 11 times 11 factorial, well, that would have been a much bigger number now. Well, I'm sorry, a much smaller number. Bigger number in the denominator, but smaller number as a ratio, as a fraction. So these terms are basically negligible. So this one here is a pretty good approximation. And I don't know about you guys, but I would prefer to do this one here rather than the midpoint rule or trapezoidal rule or Simpson's rule. Although that one wasn't too bad, you could have used your calculator, but I don't know, I find this one here a little bit more engaging, I would say. Okay, now let's go ahead and take a look at one more problem here. So for this one, we're being asked to find out, okay, well, what is the power series for f of x equals to the arctan of x centered at x equal to 0? Now for this one, well, we'll determine the interval of convergence as well. Now before we begin this problem, I want to add an extra piece of information, and I'll put this one here as a hint. I want everyone to know the power series representation for the function 1 minus x. This power series is going to be the same thing as the sum as n goes from 0 to infinity for x to the n, which means that I would get here a 1 plus x squared plus x cubed, and so forth. Now this one here is having a radius of convergence that's less than 1. Okay, now why do I want you guys to know this? Well, because this problem here is, or it could be a little bit tricky, because, okay, do we want to come up with a power series? Then we would have needed to figure out, okay, what's the function value valued at 0, then the first derivative at 0, and so forth and so forth. But I want to see if I can take some shortcuts, and the shortcut that I'm going to take is going to be involving this power series. Now, how are we using this shortcut? Well, I want you to remember that if I have the arctan of x, what happens if I take the derivative? Well, if I take the derivative, this one will be a 1 over 1 plus x squared. Now, notice here that the 1 plus x squared, okay, is looking somewhat similar to the 1 over 1 minus x. Not quite the same though. So how can we use a hint? Well, to be honest, I gave you guys this hint for extra practice to take advantage of the fact that if you know one series, if you can maybe make the other series look like the other one, or I guess think of the 1 over 1 minus x. Maybe see if a function composition can help us come up with the 1 plus x squared. Then we could use this formula. Now, lucky for us, I think that we can. I'm going to think about the following u substitution. What if I or before I do the u substitution, if I rewrite this power series, the 1 over 1 minus x, in terms of u, because again, u could be any value. Think of it more as a function composition now. Then this is the power series that they were dealing with, where the absolute value of u here, there we go, is less than 1. Okay, so now with that out of the way, if I have 1 over 1 minus u, and I know that this is equals to this series, and if I want to use that series to help me figure out what's the power series representation for 1 over 1 plus x squared, I think that we can simply go ahead and let the u be equals to a negative x squared. Because if I have that one, then 1 minus a negative x squared, lo and behold, we get the 1 plus x squared. Okay, so I'm going to go ahead and use this substitution then, and say that the power series for a 1 over 1 minus the negative x squared is going to be equals to the sum as n goes from 0 to infinity for the negative x squared raised to the n, which is going to be equals to a 1 plus negative x squared plus a negative x squared squared plus, and this is the last term that I'll use, a negative x squared cubed, which is going to give me 1 minus x squared plus x to the 4th minus x to the 6th, and we just keep on going here. Okay, now why are we doing all of this? Because, I mean, ultimately we're looking for the power series representations for the arctan of x, not the 1 over 1 plus x squared. So what can we do? Well, since I knew that the derivative for the arctan was 1 over 1 plus x squared, well, I can simply go ahead and integrate this one here with respect to x. And now we know here then that the arctan is the integral of 1 over 1 plus x squared. So now all that we need to do here is figure out, okay, well, what is now the antiderivative or the integral for the 1 minus x squared plus x to the 4th minus x to the 6th and so forth. So we're going to get here then, now at this point, guys, I'm just going to go ahead and figure out the integral, and we're going to get the arctan of x is equals to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7 over 7. We would keep on adding terms, and then the c, our constant of integration. Okay, now, what about this constant of integration here? What can we do with it? Because we didn't encounter it in the other problem that we did the integral, because it was a definite integral. So what can we do here? Well, remember that we were centering our power series at x equals to 0. So at x equals to 0, what do we get? Well, at x equal to 0, we're going to have the arctan of 0. And this one here is going to be equals to, well, now what do we get on the right-hand side? If all our x's are 0, well, then this is all one big 0. But what about our c value, though? Is that one 0? Well, let's see. I mean, it will be, but let's see. All right, so if I have the arctan of 0, it's equals to c. However, what is the arctan of 0? Well, the arctan of 0 is 0, so that means that the c, it was actually 0. Okay, so then now we know how the arctan is looking like. The arctan of x is going to be equals to the series as n goes from 0 to infinity. Okay, so what pattern do we see here? Well, I do see some alternating signs, so I'll put it here as -1 raised to the n times an x. Now what about the powers of x? Well, we have a 1, a 3, a 5, and a 7. So it looks like we have odd powers, so that means that I should have a 2n plus 1. Does that match? Well, when n is, let's say, 3, if n is 3, I have 2 times 3 is 6, plus 1 is 7. Okay, so that works. And we're dividing, again, by odd numbers, so we're going to have here a 2n plus 1. Now, keeping in mind, though, that if I'm starting my series at n equals to 0, this is n equals to 0, this is n equals to 1, this is n equals to 2, and this one here was n equals to 3. Okay, so we now have the power series representation for the arctan of x. Now this problem here was also asking us to figure out, okay, what is the interval of convergence? Now we know here that the radius of convergence was 1, so it's just a matter of figuring out, okay, are the endpoints included in the interval of convergence? Now for this problem, it turns out that it is, but this one here, I'll not do it, I ran out of space. However, I'll let you guys verify that the interval of convergence is the closed interval from -1 to 1. So the endpoints are included. And again, I'll let you guys verify it here. Alright guys, now this is where we're going to be stopping our recording. There is one more example, but to be honest, as I mentioned in class, sections 11.1, 11.3, and 11.2, they are all very closely related. And I want to focus on examples like this in the video lectures for section 11.3. Alrighty, so this is where we're going to be stopping, and I'll see you in the next recording. Have a good one.